Hey, this is Horner, and this is 2001 number 2, and this one's all about momentum. So first thing we need to do with this one is just notice what's happening. We do have a ball rolling across the table, hits another ball, knocks that ball down, and then it does say the first ball when it's coming in hits that ball and then comes back this way with a speed of 0.7 meters per second. So we're going to make that negative 0.7 and make this positive, which should make the speed of this ball positive. And that's what we want. So we want to know what is the speed of the target ball. This is definitely a elastic collision, so we know that it is elastic. And because of that, we're going to use our equation m1 v1 original plus m2 v2 original. Now notice this one is 0, so we can just leave it off there. Is equal to m1 v1 final plus m2 v2 final. So let's go ahead and plug everything in. Mass of the first ball is 0.1. Speed of the first ball is 1.4 in the positive direction, which is right. That's equal to m1 v1 final. So that's 0.1 times, and remember the final speed of that first ball is negative 0.7 plus mass of the second ball, which is 0.5. And then we're trying to find out what is the final velocity of that second ball. Now that we've plugged everything in, we can go ahead and do our math. So this one ends up being 0.14 is equal to, and then we've got our next one here, which should be this is equal to negative 0.07 plus 0.5 times our final velocity. If I take 0.14 and then I add to it, it looks like, I don't subtract it, I'm going to add this to both sides. I'm going to add 0.07, so I get 0.21 is equal to 0.5 times V2F. And now I'm going to get out my calculator so I can figure out what that is. And I'm going to take 0.21 and divide that by 0.5, and I end up with 0.42. So V2F is equal to 0.42 meters per second, and that is the correct answer. For letter B, it says the tabletop is 1.2 meters above the level horizontal floor. The target ball is projected horizontally and strikes the floor at a displacement. So here's the displacement. They want us to find out what is this displacement. So one of the things that we need to do first here is we need to figure out which equation to use. And so this one's pretty easy because I know that the distance in the y is equal to the original distance in the y plus the original speed times time plus 1/2 a t squared, where a is really g and g we know is negative. So our final position is 0. Our original position is just the height of the table, which is 1.2 plus, and then we've got our original speed, which is 0 times the time, plus 1/2 of negative 10 times t squared. Now at this point we can solve for t, and t should be equal to somewhere around about 0.49. So whether you use 9.8 or 10, you're going to get the same thing. Now we can substitute in. So we're going to say distance is just equal to our velocity times time. We know our original velocity should be equal to that 0.42 meters per second we found earlier. And then we're going to multiply that times our time, which is 0.49 seconds. At this point we're done and we get an answer of 0.21 meters. For the next part, which is letter C, they want us to go through and let's see what they want us to find for letter C. They want us to look at this situation where now the ball is coming across and it strikes this other ball at a glancing angle. So it's going to hit it near the top, near the side, so kind of right in that area right here. And this time it says that the second ball comes off the table. We're looking down at the tabletop, comes off at a angle of 30 degrees with a speed, and the distance that it falls here going left to right. So this would be along the floor if you want to measure that. So a point down at the bottom all the way across would be 0.150 meters. So that's its horizontal displacement. So if we were looking at the side of the table, so here's the table, if we're looking at the side of the table, this distance right here would be that 0.15 meters. They want us to find the speed of the ball again, so we're going to say the speed of the ball C is equal to, because notice this is now about C, is equal to the distance divided by the time. We have a distance of 0.15 meters, and we know that the fall takes 0.49 seconds. So we end up with 0.31 meters per second. So that is the speed of the target ball C immediately after the collision. So that one's pretty easy to do. The last part that they want us to do is they want us to find out what is the y component of the incident ball's momentum immediately after the collision. And so they make it easy for us by labeling what's x and y. So you'll notice that the x direction would be directly off the right side of the table and the y direction would be up. So they want to figure out where does that A ball go. So our momentum here is conserved in the y direction. So we're going to say that the momentum of ball A in the y direction plus the momentum of ball C in the y direction, that should equal 0 if they are conserved, because they need to be equal but opposite. So let's rearrange this. We're going to say that the momentum for A in the y is equal to negative times the momentum of C in the y. Let's talk about the momentum of A in the y direction. So for A, we were going 1.4 meters per second. We were going 1.4 meters per second, and we see that it strikes C, and C goes off in this direction. We know this should be equal to the mass of C times the speed of C, but we see that because it's conserved, let's go ahead and figure out in the y direction, that would be this side. If we go ahead and extend this triangle out, we can extend the triangle out. That would be this side. We need to find out what this side is, because if we know this side, then we know the same thing for the other ball. So ball A is going to follow in this direction, while ball C goes in the direction that we've got here, which is down to the right. Ball A is going to go up and to the right. So this is going to be times the sine of 30 degrees. And so the momentum for A should be equal to 0.015 kilograms meters per second. So what we did here was we said that the mass times velocity of C coming this way, if we do the sine of this angle, we're really going to find this side, which is equal to the momentum of C in the y direction, but because the momentum of A in the y direction should be just the opposite of that, we know that the momentum of A in the y direction is the same number value. So all it is just the number itself. So that's why this one is the way it is. And that is the end of this problem.